Good afternoon, class. Today I will speak about one of the topic of material science subject, that is ferrous alloys. This topic comes under unit 2, and this topic is studied by various second year students studying material science subject. So these are the topics which we will study. First topic is the allotropic transformation of the pure iron, then the iron carbon diagram. After that, different phases of iron carbon diagram, features of iron carbon diagram, and the various reactions occurring in iron carbon diagram, and so on. We will study about the various microstructures of eutectoid steels, hypoeutectoid steels, and hypereutectoid steels. So coming on to the allotropic transformation of pure iron, what actually comprises of allotropy means? Allotropy is the branch of science which actually defines how the iron properties are changing with respect to the change in the temperature. See, you can see here that there are various allotropic forms of iron. First is the alpha iron, which is in a BCC structure, and this is magnetic. Going above 768 degrees centigrade, we find that this alpha iron loses its magnetic properties, so it becomes non-magnetic. And this is the temperature at 768 degrees centigrade at which this iron loses its magnetic properties. This temperature is known as Curie temperature. Then going above 910 degrees centigrade, this iron converts into gamma iron and its structure is FCC. This is also non-magnetic. Above 1401 degrees centigrade, this gamma iron converts into delta iron. This is BCC structure, and the melting point of pure iron is around 1535 degrees centigrade. Above this temperature, this iron, solid form of iron, converts into the liquid stage. So this graph actually shows the variation of temperature of iron with respect to the time, and this is the horizontal line which actually denotes the temperature latent heat of vaporization. Then study about the iron carbon diagram. In most of the book it is written iron carbon diagram, but it is not actually the fact. The correct pronunciation for this diagram is that the iron and iron carbon diagram. Iron and iron carbide diagram. Iron carbide diagram stands for Fe3C and iron stands for Fe. So the pronunciation for this is Fe3C diagram. So this diagram actually shows the map of temperature at which different phases changes occurs on very slow heating or cooling with relation to the carbon. Actually on x-axis carbon percentage is going to be increased, and on y-axis temperature is going to be increased. And in this graph we actually show how the various phases of iron at a different temperature. So iron carbon diagram actually shows the type of alloys formed under very slow cooling, proper heat treatment temperature it actually shows, and how the properties of steels and the cast iron can be radically changed by the heat treatment. As you know, when you increase the percentage of carbon in the iron, then the melting point of iron starts decreasing. So one of the phase is ferritic phase. This ferritic phase is also known as alpha solid solution, and it is the interstitial solid solution of a small amount of carbon dissolved in alpha iron. So these carbon particles actually goes into the interstitial sites of alpha iron and form the ferrite phase. And the stable form of iron of ferrite is below 912 degrees centigrade, and the maximum solubility is around 0.025% carbon at 723 degrees centigrade, and it dissolves only 0.008% carbon at room temperature. It is the softest structure that appears on the diagram. You will not find out any phase mixtures of the iron which is more softer than ferrite. So this is the pearlite is actually the phase mixture. It is not the phase, it is a mixture of two phases. First phase is ferrite and second phase is cementite. It is very fine plate-like or laminar mixture of ferrite and cementite. Pearlite is actually the eutectoid mixtures containing 0.80% carbon and is formed at 723 degrees centigrade on very slow cooling. So the pearlite actually formed at around 0.80% of the carbon, when 0.80% of the carbon is dissolved in iron. And you can see here this is the structure of pearlite, and this white background actually shows the ferrite, and this columnar structure actually shows the cementite. The white ferritic background or the matrix contains thin plates of the cementite. Then the second phase is of iron is austenite. This is one of the versatile phase which exhibits many different properties which is useful for the human beings. But the real problem with austenite is that this is not stable at room temperature. It is actually stable above 728 degrees centigrade. Austenite is an interstitial solid solution of carbon dissolved in gamma iron, and the maximum solubility is around 2% carbon at 1130 degree centigrade, and it is high formability. Most of the heat treatment begin with this single phase, and it is normally not stable at room temperature, but under certain condition it is possible to obtain austenite at the room temperature by various heat treatment processes. Then another phase of iron is the cementite. It is the hardest structure that appears on the iron carbon diagram, and the exact melting point of this phase we actually doesn't know. Cementite is also known as iron carbide, which stands for Fe3C, which is very hard, brittle, intermetallic compounds of iron and carbon, which contains 6.67% of the carbon. It is its crystal structure is orthorhombic, and its tensile strength is very low, which is around 5000 psi, but its compressive strength is very high. Then second phase mixture which is present in this iron carbon diagram is the ladoberite. First is the pearlite, and second phase mixture is the ladoberite. Ladoberite actually consists of eutectic mixture of austenites and cementite. So it actually contains 4.3% carbon and is formed at around 1130 degree centigrade. Then another phase which actually exists in iron carbide diagram is the martensite phase, and the martensite phase a supersaturated solid solution of carbon in ferrite we actually see. This type of phase we actually see when the temperature is very low, and we do the cooling of any steel so rapidly that it converts from austenite phase to the pearlite phase. That it's converted from austenite phase to the martensite phase, and the pearlite formation of pearlite phase is suppressed. Why it is suppressed? Because we actually cool down this austenite phase so rapidly that the formation of pearlite doesn't happen. The interstitial carbon atoms distorts the BCC ferrite into a BC tetragonal structure, which is responsible for the hardness of the quenched steel. As the quenching is done in order to form the martensite structure, that's why the hardness of this type of phase is very high. So this is the final iron carbon diagram which you actually see in here. The y-axis actually shows the temperature in degree centigrade, and x-axis shows the percentage of carbon. As we go on increasing the carbon percentage, you will see that the temperature of iron gradually starts to decrease, and at 4.3% carbon you see that the temperature of iron carbide is around 1147 degrees centigrade. Above this line, this curve, this is the liquid phase of iron is there, and you can see here that there are three different horizontal lines, which is very important in order to construct this iron carbon diagram. First line is this one, and here actually eutectic eutectoid reactions actually occur, and second line is this line 1147 degrees centigrade. Here eutectic reactions actually occur, and third line is 1493 degrees centigrade. Here peritectic reaction is going to occur. So the different phases you generally see in this diagram are: first phase is the alpha phase, which is occurring here. Second is the gamma phase, gamma austenite, and third is the delta ferrite. Alpha ferrite, gamma austenite, and delta ferrite. Martensite actually occurs in this range, and this is the cementite. These are the five different phases which actually occurs in iron and iron carbon diagram. So you can see here that the maximum solubility of austenite phase in maximum solubility of carbon in austenite phase is around 2.14%. Similarly, you can see here that the maximum solubility of alpha in carbon is around 0.0022%. And here you can see that Fe3 stands for cementite, and you can see that here is the liquid and here is the delta. So here liquid plus delta will form, and here is delta gamma, and here is a delta ferrite. So here you will see delta plus gamma. So when you cool at this temperature, this liquid converts into gamma plus cementite, and here when we cool from this point to this point here, then this gamma converts into alpha plus Fe3C. The mixture of alpha and Fe3 is known as actually the perlite, and the mixture of gamma and Fe3C is known as laddeborite. These laddeborite and perlite are actually the phase mixture. These are not the phases. The phases actually are this alpha ferrite, gamma austenite, delta ferrite, cementite, and martensite, whereas laddeborite and perlite are actually the phase mixture which we generally see. So these are percentage 2.14%, 4.30%, 0.76%. These all percentage you have to learn, because in order to construct this diagram, this percentage of carbon is very important in order to find out that where different types of phases are actually occurring. So you can see here that beyond 2.14% cast iron is there, and below 2.14% we actually see the steels. So below 0.76%, here this type of steel is known as hypoeutectoid steel, and beyond 0.76% and below 2.14% we actually see the hypereutectoid steels. Similarly, from 0.14% to 4.30% you see the eutectoid steels, and here hypereutectoid steels. So here cast iron is there and here steel is there. So one point shows the eutectic reactions and another point shows the eutectoid reactions. So these are various features of iron carbon diagram, and these are the three reactions which actually occurs: peritectic, eutectic, and eutectoid. In peritectic, liquid plus delta converts into gamma. So you can see that liquid plus delta converts into gamma. This is liquid plus delta converts into gamma on cooling, or liquid or gamma converts into liquid plus delta on heating at 1493 degrees centigrade. So you can see here that at 1493 degrees centigrade, 1492 degrees centigrade, this delta plus liquid converts into gamma on cooling. Similarly, at this eutectic point, this liquid converts into gamma plus Fe3C. gamma plus Fe3C. And this eutectic reaction is actually occurring at around 4.30% of the carbon, and temperature is 1147 degrees centigrade. So 1130 degrees centigrade, 4.3% of carbon, we actually see the eutectic reactions. And the alloy which generally formed is the cast iron. Similarly, eutectoid reactions are those reactions in which gamma phase converts into the perlite phase. Perlite phase actually consists of alpha plus Fe3C, and this type of phase you generally occur at around 727 degrees centigrade, and carbon percentage is 0.76%. So you can see here 723 degrees centigrade, and at 0.8% weight of the carbon, we see the phase mixtures which consists of ferrite and cementite, and this ferrite and cementite is known as perlite, and these alloys are known as steels. So you can see that in peritectic reactions, here delta phase is forming, here liquid is forming, here delta plus liquid, here gamma. So on cooling, this delta plus liquid converts into austenite. Delta carbon percentage is 0.10%, liquid percentage is 0.50%, and the austenite percentage is 0.18%. So this percentage is 0.18%. Similarly, actually peritectic reactions occurs at those points where two different materials makes an alloy when their melting point temperature difference is very high. There we generally see the peritectic reactions. Then second is the eutectic reactions. In eutectic reaction, liquid converts into ledoborite, austenite plus cementite, and this reactions actually occurs at around 1130 degrees centigrade, and the carbon percentage for liquid to convert it into austenite plus cementite is around 4.3% on cooling, and the ledoborite mixture is austenite, that is 2% maximum dissolvability of carbon, and cementite maximum dissolvability of carbon is around, we actually see at around 6.67%. Then the third invariant reactions is the eutectoid reactions, at which austenites converts into perlite. Perlite is ferrite plus cementite. So austenite is 0.8%, here this carbon percentage is 0.8%. On cooling it converts into ferrite, and the ferrite maximum carbon solubility is 0.025 here, 0.025, and cementite 6.67% we see here. So this reactions is known as eutectoid reactions or eutectoid mixtures by combining this ferrite and cementite. So iron carbon diagram, the diagram shows three horizontal lines which indicate the isothermal, that is constant temperature reactions, whether on cooling or on heating. First horizontal line is at around 1492 degrees centigrade, where peritectic reactions take place, in which liquid plus delta converts into austenites. Similarly, second horizontal line is at around 1130 degrees centigrade, where eutectic reactions takes place, and here liquid converts into austenite plus cementite. Then the third horizontal lines is at 723 degrees centigrade, where eutectoid reactions take place, and here austenites converts into perlite on cooling, and this perlite is a mixture of ferrite and cementite. Then coming on to the studying the different types of microstructure of eutectoid steels, hypoeutectoid steels, and hypereutectoid steels. Firstly, we will study the microstructure of the eutectoid steels. So you actually know that the eutectoid reactions actually occurs at around 723 degrees centigrade, and the carbon percentage is 0.8%. So this is the invariant point at which this eutectoid steels we generally used to see. So we draw one vertical lines here, and we actually draw x-axis, x dash, and one point is A point, second point is B point, and this A point comes under the region of this, and this B point comes under the region of this and x dash. So this A point shows, this is the microstructure of A point, which actually shows the austenitic phase. Here except austenite nothing is there, and the austenitic phase is generally shown in this manner. But as you cool down from austenitic phase to perlitic phase, so you will see the perlitic diagram microstructure. Actually perlitic microstructure consists of alternate layer of alpha ferrite and cementite. So you can see that the alternate layer of alpha ferrite and alpha and Fe3C is shown here. Similarly, microstructure of hypoeutectoid stills, as I have already told you that below 0.8% carbon, we actually see the hypoeutectoid stills. So so below 0.8%, wherever you draw one line, so you will see three different regions: first region, second region, and third region. So first region, here you will see that the same austenite phase is there. Then on cooling down, here you will see that there is alpha, here is austenite. So here alpha particles starts to nucleate from the gamma particles. So here you will see, starting at the boundary lines, you will see that the alpha particles is going to nucleate. Then upon more cooling and just below this line, you will see that this nucleation starts to grow in a very fast manner. So you can see that these small circles takes the shapes of some boundary like region, so that it starts to grow and makes its own region. On more cooling from E point to F point, you actually see this type of structure, which actually shows the perlite structure. Perlites are those why this structure is known as perlite, because when you actually see this type of structure under the microscope, you will see that it is like a pearl. How the pearl shines, in the same way this type of structures actually shines. So you can see that the alternate layer of alpha ferrite and cementites is there. Similarly, the third type of microstructure which you generally see here is the hypereutectoid stills. In hypereutectoid stills, you always draw the one alloying line at carbon percentage greater than 0.8%. So you can see that first region is this, second region is this, and the third region is this. First region is above this line, so here gamma austenite is there, so same structure is going to occur here. Gamma plus cementite both are there. That's why this cementite Fe3C starts to nucleate, and as you cool down the temperature from H point to this I point, then this Fe3C continues to grow, and you see the proeutectoid phase, and this is the final microstructure which you actually see at this point below 723 degrees centigrade. So this is the microstructure of hypereutectoid stills. Similarly, this is the complete microstructure diagram of iron and iron carbon diagram, where different phases of iron is actually shown here. So you can see here that this is the gamma austenite phase, which actually shows the same structure, and here alpha ferrite is there, here one austenite is there, here nucleation, alpha nucleation is going to start, here perlite is going to form, and you can see that from below 0.76 degrees centigrade hypoeutectoid still, 0.76 to 2.14% hypereutectoid stills, from 2.14 to 4.30 you actually see the hypoeutectic stills, and from 4.30 to 6.67 you actually see the hypereutectic cast iron. So from 2.14% to 6.7% you actually see the cast iron composition. And one more thing, in this diagram you actually see that these line 727 degree temperature horizontal lines is actually denoted by the A1. This curve is denoted by ACM. This curve is denoted by A3. So different lines have different namings corresponding to what type of phases is going to occur when you heat certain component from higher temperature from lower temperature to at higher temperature, or you cool down certain components from high temperature to lower temperature. So different types of structure is going to see in this iron carbon diagram at different temperature and at different carbon percentage mixtures. So with the help of this diagram, you can easily predict different phases of this iron, starting from gamma austenite to alpha ferrite, delta ferrite, martensite, and cementite. Apart from these, you also see two phase mixtures. One is perlite and second is the laterite. Thank you, class.